Hi everyone, I'm Peter Zhao, and today I'll be presenting on the gonality of random graphs. So here is just a quick overview on the format of the presentation, and if at any point you feel like you want to refer back to this outline just for a refresher, please feel free to do so. So I'm just going to jump right in. So we're going to start with a crazy sounding question and an answer to that question, and then we'll spend the rest of the talk trying to understand what all of the different words and symbols mean, defining different concepts, and ultimately end up proving this theorem that we're trying to prove. So in 2014, Andrew DeVoe, David Jensen, who coincidentally graduated from Williams in 2004, Jenna Keinig, and Dan Mitropolsky asked what the gonality of an Erdős-Renyi random graph is. The motivation for this lies in the study of algebraic curves and Brill-Noether theory, which is beyond the scope of this presentation, but definitely interesting to look into if you're familiar with these topics. The theorem they proved states that the expected value of the gonality, which is kind of written as G of NP, which is an Erdős-Renyi random graph, is approximately n. You might also wonder what this precondition is that states let Pn equals Cn over n, and suppose that Cn is which is a lot less than n, is unbounded, means. So this precondition simply maintains that the graph has certain nice properties that help in proving the gonality. So now I'll dive into the various definitions and symbols to explain what all these details are and what they mean. We'll first start with a little intro to graph theory. So a graph theory is just the study of graphs, and a graph is denoted as G of VE, where V is just a set of vertices, or in these examples, the little dots, and E are just edges between these little dots. We'll assume, for the purposes of this talk, that all graphs we want to consider have three important features. They're all simple, undirected, and connected. Now, you might be wondering what this all means. All this means is that simple graphs are graphs that do not contain any loops or double edges. So I can start in a vertex, and if I look at all its neighbors, there are only one edge to every single neighbor. And each pair of vertices share at most one edge. Undirected means that the edges do not have a specific direction. I can start on a vertex, walk to one of its neighbors, or another vertex connected by an edge, and then travel back to this original vertex along that same edge. And lastly, connected means that the entire graph is one whole piece, and every vertex is reachable by some path of edges to every other vertex. So here are some examples of valid graphs that we would like to consider, as well as some graphs that are non-examples. Again, all of these graphs that are displayed on the screen right now are all valid graphs, just depending on how you want to define graphs for your certain problem. So these three graphs are connected, simple, and undirected. The bottom three graphs, this first one fails on the fact that it's not connected. You can see that it has two distinct parts. And if I consider any of the vertices on the left chunk, there's no possible path that gets me to the right chunk. Okay. For this graph in the bottom middle, we see that in the three of the vertices on the top, they share two edges between them, which is kind of just not allowed in our setup. Still a reasonable graph, just not what we want to consider. Lastly, this graph has directed edges. As you can probably see, if you look carefully, that each edge has a small triangle at the very end, which just represents the directionality is pointing in. So if I start on this very first vertex on the very left, I travel along, I can't actually go back on the same edge. And actually in a specific graph, I actually can't get back anywhere in any way because of the directionality of each of the edges. Okay, so now that we have a bit of graph theory under our belt, I'm going to move on to explaining what the gonality is, what the gonality of a specific graph is. So I'll first introduce this game called the chip firing game. So the chip firing game is set up as follows. So first, start with a simple, undirected, and connected graph, just like kind of the examples we explained earlier. And this represents kind of like the board or like domain of our chip firing game. Next, we shall place an integer number of chips on each vertex of G. This integer number can be positive or negative. And this placement of chips in a certain way is called a chip configuration. So here I have a chip configuration such that I have 6 negative vertices on the very left and 11 other vertices on the other nodes. Okay, so you might be wondering, how do we play this game? So to play this game, we want to perform what we call chip firing moves. What this means that if we chip fire a vertex, we move one chip from that vertex along all of its edges. So for example, in this graph, if we fire the top middle vertex with 6 chips, which sends one chip along each of its edges, we remove 3 from this top vertex, and we add 1 to each of its neighbors, which are the bottom 3 vertices. So in this case, we have 1 plus -1 equals 0, which we don't write anymore. 2 plus 1 equals 3, and 3 plus 1 is 4. So that's how many. So that's how many chips we have in our new configuration. And we can call 2 chip configurations equivalent if they differ by a sequence of chip firing moves. For example, so these 2 configurations are equivalent because they differ by a single chip firing move. If I had chip fired this top vertex again, the same one that I fired before, then I'll send 1, 1, 1 again to each of its neighbors. And it ends up being that I get 0 up here, 1, 4, and 5 on the bottom vertices. And this configuration is still equivalent to the previous 2, again, because it differs only by a single chip fire move. And I can have as many chip fire moves in sequence as I want. Okay. And just as a note, we can also chip fire vertices that contain less chips than the number of edges they have. That vertex just simply goes into dead or has negative value. So for example, in this first graph, if I had fired this bottom vertex 2, it will still be forced to send 1 chip along each of its edges, but the remaining value would then just be -1, which is totally fine. There's no rule saying that we can't have negative value. We can't create negative value. So kind of the main goal of this game is whether or not we can remove all the debt or the negative valuation from this graph, or from this chip configuration. So here I have kind of like the ending configuration of one potential ending configuration that wins this chip firing game. So if you wanted to pause and see if you can figure this game out, feel free to right now. I'll be right back after you're done. Okay, so moving on. So now I'm going to kind of dive into how the chip firing game relates to Gonality. So we're also going to frame the Gonality as a game called the Gonality game, which is actually just a special case of the chip firing game with a very specific set of rules and gameplay. So the setup is as follows. You start with k chips on a graph. So you're given a graph, and then you have a non-negative integer k, and you want to place k chips on the graph however you want. So here I have 7 chips, and I've placed it arbitrarily like this. And after I've done placing down my chips, my opponent will then place a single dead chip anywhere on the graph. And so your goal is to then clear all the debt from this chip configuration through chip firing moves. So it's basically the same thing as a chip firing game, except there's this condition that we first place on our chips, and then our opponent places a chip down, and then they only place 1 chip. So I'm actually going to play this Gonality game out. So what I'm going to do is my first step is I'm going to fire this bottom right vertex, which sends 1 chip along each of its edges, giving me 0 chips on this vertex, 1 plus 1 chips here, 1 plus 1 equals 2 chips here, and 1 chip here. So this is our new graph, or new configuration. Now what I'm going to do is going to perform a chip firing on a subset of the vertices. Now, the reason, so what does that mean actually? So I'm going to say that I can fire this subset of vertices all at once. So the reason we're allowed to do this is that imagine I'm just considering maybe 2 vertices arbitrarily in the graph. And if I fire one and I send a chip over, and then I fire the next vertex immediately and send a chip back, effectively the edge between the 2 vertices cancel out and no movement of chips actually happens. So we can actually kind of generalize this idea and say that if I fire a whole subset, all the edges within a subset basically don't have any transferred chips. Only these edges out that are leaving the subset actually send chips. So in this case, what happens is that there might be a lot of chips being firing within this subset, but the only actual things that happen is I send 1 chip here, 1 chip here, and 1 chip here. This is a very useful concept for just kind of describing kind of chunks of chip firing moves and by kind of the equivalence earlier, I know I'm allowed to do this sort of thing. Okay, so it's going to fire kind of towards the complement of the subset, and we end up firing 1 from here, which gives me 0, 1 from here, which gives me 1, and 1 from here, which gives me 1. And I send 1, 1, 1 along each of these edges, which gives me 3 minus 1 equals 2. And so kind of I've just shown that we were successfully able to clear all the debt on this Gonality game, and we've won the Gonality game. Okay, let me clear all the drawings and kind of now define what the Gonality is. So the Gonality of a graph is the smallest number of chips you can place so that you'll always be able to win regardless of where your opponent places their dead chip. So you can so kind of what you have to do to show that a graph has a certain Gonality, I have to check every scenario with smaller and smaller numbers of chips, or k, and kind of check every scenario where I place a certain number of chips down, my opponent places it anywhere, and show that I can at least win one of them. Or in a case where the Gonality kind of flattens out, I cannot win any configuration. Now, this is kind of like an exhaustive checking, and you can imagine this is a pretty difficult thing to do. So if I just go back to the example before, you might wonder, so I was able to win this Gonality game with 7 chips. Could you possibly do less? Yeah, so feel free to pause if you kind of like to try to figure this out, maybe try to determine the Gonality of this graph. I'll just move on and leave it up to you guys as an open question. Okay, and Gijwit, Smit, and van der Wegen in 2019 showed that computing the Gonality is NP hard. So this is kind of like a quantification of the difficulty. If you don't really know what NP hard means, that's not particularly important. Just understand that it's a very specific measure of difficulty, often used by mathematicians or computer scientists. Okay, so now we've shown that finding the Gonality is difficult. Remember our original question was, what is the Gonality of a random graph? And you might be wondering, what is a random graph, and how do we even determine the Gonality of something that's kind of non-deterministic and random? Okay, so an Erdős-Rényi random graph is kind of, so far we've only defined concrete graphs. You know, we've actually been able to draw them and say like, oh, this is a certain graph. Now, an Erdős-Rényi random graph is a model. It follows the Erdős-Rényi model for random graphs because there's many different types of random graphs. But in this model, which is actually named after 2 famous Hungarian mathematicians, Paul Erdős and Alfred Rényi, who specialized in combinatorics, probability, and graph theory, and among other fields. What this model says is that I'm going to give it 2 numbers, n and p, where n is the number of vertices and p is the probability and edges contained in the graph. So to construct this graph, I will place down n vertices, and I'm going to look at the set of all possible edges in which there are n choose 2 of them, because edges are defined by 2 vertices. So for each of these n choose 2 vertices, I'm going to have a coin with probability p that it lands on heads and probability 1 minus p it lands on tails. And I'm going to, for each edge, I'm going to flip this coin. If it lands on heads, I'm going to include it in my graph. Otherwise, I do not. And so this kind of gives us a certain looking graph. And here are just kind of 3 examples of potential Erdős-Rényi graphs on 5 vertices. Quickly do note that this first graph is actually disconnected, which in our study of Gonality is actually not something we want to consider. So we want to consider what looks more like the 2 examples on the right, which are connected and likely have similar numbers of p. This first one might have a smaller value of p. We're not too sure because I kind of just drew it out. So again, we want to consider connected versions of g of np. Okay, now since we've defined kind of all the bits and pieces that were part of the initial questions we were trying to answer, I'm going to kind of start diving into the proof of the Gonality of a random graph. So what I'm going to do is I'm going to first define, kind of show the upper bound on a Gonality, then show the lower bound on a Gonality, and then combine these 2 pieces together to give me a concrete value for the Gonality of a random graph. Okay, so we'll first start with the upper bound. So first, we will show that the Gonality is bounded above by n minus little o of n. So to be clear, if you're not familiar with this notation, I'm going to kind of give it a little explanation. little o of n is defined such that if we have two functions, f of n and g of n, f of n is little o of g of n if this holds, such that if I take the limit from n going to infinity of f of n over g of n, this limit goes to 0. And that's just kind of defined this way. And if you take a step back and see what this actually means, it just means that asymptotically, little o of n is a loose upper bound for f of n. And so this notation kind of describes asymptotic behavior. So we only care about it when n becomes large, which is kind of a natural way to study probabilistic structures, since we care about the expected value rather than like at any certain size. Okay, so I'll kind of clear this definition out. Close my annotation. Okay, so we will start with the following theorem to show this is true. If a graph G is a simple graph on n vertices, then the gonality of the graph is bounded above by n minus alpha of G. Now you might be wondering what alpha of G is, and it is the independence number or the size of the maximum independence set, which I'll explain what it is right now. So an independent set of a graph is a set of vertices such that no two are connected by an edge. And the independence number is a maximum size set. Sorry about that. It's a maximum size set. The maximum size of all possible independent sets for a certain graph. So consider the following graphs, each with a maximal independent set. Notice that the independent set on the very left and the very right have only size 2 because there's only 2 vertices. And you can manually see that I cannot include any other vertex in this configuration. Otherwise, it's connected via a possible edge. If I try to choose this one, it's connected to this top one. If I try to choose one in the middle, it's connected to this one. Okay. However, the two independent sets in the middle happen to be maximal. And the way to kind of confirm this is that you kind of exhaustively have to check all possible independent sets, which you can imagine is quite difficult. It's also been proved that computing the independence number is also NP hard, but we won't really worry about that because we're going to be using it as a tool to help us determine the gonality. Okay, so now that we know what an independent set and independence number are, let's dive into kind of proving that the gonality of a graph is bounded above by n minus its independence number. Okay, so let's set up the gonality game as we have before, and let I be an independent set of maximum size, so size alpha of G, and place a chip on every vertex not in I. We'll just call this sum of this chip configuration D. Okay, so now we've placed down our chips kind of in this kind of format. We placed one on every black. So the red vertices form the independent set, and the black ones form just the rest of the vertices. So consider our opponent's placement of this dat chip now, and we'll call this V. So if the placement is not in the independent set, then we immediately win because we already have one chip on every single one of these vertices. So they just kind of cancel out and we immediately win. If V is actually in the independent set, then since all the neighbors of V are not in I, we can fire all other vertices to neutralize this det and win. So what this means is that like in any situation, the chip that has the det will always be, which is this one, will always be, all its neighbors will always not be in the independent set by definition. That's kind of how we construct an independent set, right? They're not, none of the vertices in the independent set are connected to each other via an edge. So what I can always do is that I just fire everything else. And when I fire everything else, I know that the edge is leaving the subset to the V. I'm just call this V. I know that they always have one chip on them. So I send one chip along each of these. So this gives me 3 minus 1 equals 2. And so we win the gonality game. And so you can imagine that I can always do this sort of kind of construction. And this thus gives me an upper bound because I can also see that I can probably get away with less. So clearly, if I didn't have this chip on this bottom right 1 in the middle square, then we still win the Gonality game. But at least this forms an upper bound, and we can know that for any arbitrary graph, this can always work. So now moving on, there's some scary notation on this slide, but don't fear, as I shall explain everything. So let Fn be this very long expression, Q over Pn times log C of n minus log C of n minus log 2 plus 1. It's actually not super important what that means, so we'll just treat it as a black box. So in 1990, Frias determined that the independence number of a random graph minus f of n, this long expression, approaches a very small term with probability 1. We can effectively assume then that the independence number of a random graph is bounded above by f of n. Now we can apply Frias's lemma and the previous theorem we proved earlier about the Gonality being bounded above by n minus alpha of g. And we can show that with high probability, the Gonality of a random graph is bounded above by n minus f of n, n minus f of n. And this is because the independence number is greater than fn minus epsilon by Frias's lemma, and we can replace fn with the independence number of g as we are subtracting. And we conclude that the Gonality of a random graph is bounded above by n minus alpha of the random graph. And we can now rewrite, and so that's kind of what this expression is kind of saying, n minus f of n bounds the Gonality above. Now, we can rewrite alpha of n as little o of n by the definition of little o that we described earlier, since alpha n forms a loose upper bound for n. And we can show that the Gonality of a graph is bounded above, the Gonality of a random graph is bounded above by n minus little o of n. Okay, now we will show the Gonality of a random graph is bounded below by n minus little o of n as well. This proof will rest on two key lemmas. First, consider this lemma presented by Van Daben de Bruijn in 2014. So all it states is that let G be a simple graph, then the Gonality of G is bounded above by, bounded below by the tree width. So you might be wondering what the tree width is. I'll explain it right now. So a tree decomposition of a graph is a tree whose nodes are subsets of the vertices satisfying these certain properties, such that each vertex of G is contained at least one node of T, two nodes of T can both contain a given vertex, then all nodes of the tree that in the unique path between these two nodes must contain V. And if two vertices V and W are adjacent in the graph, then there's a node of T that contains both of them. And the width of a tree decomposition is one less than the number of vertices in its largest node. The tree width is thus defined to be the minimum width across all possible widths. So that was just a lot, but the intuition is that the tree width measures how close the graph is to an actual tree. So the tree width of a tree is 1, as it is exactly a tree, and a complete graph, where the graph containing all possible edges has maximum tree width, as it is as far from a tree as possible. So in 2011, Wang showed that the tree width of a graph is bounded below, or the tree width of a random graph is bounded below by n minus little o of n with high probability. Thus, we can combine these two lemmas and see that the probability that the Gonality of a graph is bounded below by n minus little o of n as n approaches infinity is exactly 1. And this is just kind of applying this property transitively. So if I kind of sum up my original theorem, trying to show that the Gonality of a random graph is bounded below by n minus little o of n, we can again combine the two lemmas, and because the tree width is bounded below with high probability by n minus little o of n, and the Gonality is bounded below by the tree width, then the Gonality is bounded below by n minus little o of n as well with high probability. So now we have both of our pieces, kind of our upper bound and lower bound, and we can use it to prove our original theorem. So we know that the upper bound and lower bounds of the random graph are n minus little o of n, and so it follows that the expected value of the Gonality of a random graph as n goes to infinity divided by the number of vertices in the graph is equivalent to this limit expression here, such that as we take the limit from n as n goes to infinity, n minus little o of n over n goes to 1. And this is all because little o of n is defined to be a loose upper bound. So asymptotically, we can ignore it in this expression because n dominates little o of n. So if we multiply the number of vertices over, we have that the expected value of a gonality of a random graph is approximately n. So let's just take a quick step back and kind of see what this all means. So this means that pretty much we need to place a chip on every vertex of a random graph to win the gonality game on the random graph, which doesn't seem very good, as this is actually equivalent to the gonality of a complete graph, which is kind of the worst case scenario. And a complete graph is, again, a graph with all its edges contained. So to me, this seems pretty disappointing, as at least when I was reading through this paper, I was hoping that we could get something a little bit faster. Well, not a little bit faster, but a little bit less than having to put a chip on every single vertex. But it's a crazy result nonetheless, considering that the gonality is really hard to determine in general. It's NP hard, and random graphs are kind of like these little undeterministic objects that we can't really like say what they look like at any point in time. So it's a very interesting result. So I've kind of proven that the expected value of the gonality of a random graph is about n. So you might be asking kind of like what other works are related to this, and what other things have people been doing that are kind of on the same vein as this. So this year, Harp, Jackson, Jensen, and Speeder, and Jensen, again, is the same Jensen that graduated from Williams. They defined this concept known as a scramble number, which forms a stronger lower bound to the gonality of a graph given in this inequality, such that the tree width is bounded is less than the scramble number of a graph, which is less than equal to the gonality of a graph. So it'd be really interesting if someone could figure out the scramble number of random graphs, because then we would have a stronger lower bound for the gonality of, or at least a lower bound for the gonality of the random graphs as well, which I think is pretty cool. Another cool topic from Duda and Jensen in 2018 provides lower bounds on the gonality of expander graphs, which are special graphs that are sparse, which means that they're missing the majority of its edges, but has strong connectivity properties that are interesting to study. Okay, so that's kind of that's kind of the topic that I've been kind of looking at for this colloquium. Thank you everybody for coming to my talk. I'd like to thank Professor Morrison for advising me and helping me throughout this colloquium presentation and preparation, as well as introducing me to graph theory itself. I took graph theory with him back in my sophomore year, and it's opened up a lot of really interesting fields of exploration, both in math and computer science. And I also like to thank Teresa Yu, class of 2020, who just graduated last year, for helping me brainstorm this topic, as she also did a bit of research regarding gonality of graphs, and kind of she gave me a bunch of ideas for like what sorts of things I might be interested in that you really utilize my background. So if anybody has any questions or comments or feedback for me, I am more than willing to listen. So please do contact me at pjz1@williams.edu. I'll try to get back to you as soon as I can. So again, thank you so much for your time, everybody, and I hope everyone has a great rest of your week.